Okay, hi everyone, welcome to TCS Plus. Before we start our talk today, let me plug the talk that's going to happen in 2 weeks from now. So in 2 weeks from now, we're going to have a talk by Henry Wen, and he'll talk about the exciting result that MIP star is equal to RE. So that's in 2 weeks on February 26th. Today, we're really happy to have Albert Atserias with us. And he'll be talking about his recent result, or not so recent anymore, but that automating resolution is NP hard. We're really lucky to have him. This is an excellent result, and it won the best paper at Fox. So without further ado, let's hear from Albert.
Thank you very much. Thanks. So I'd like to tell you about this result with Moritz Müller. This is joint work with him on automating resolution being NP hard. And I'm very happy to be speaking at TCS Plus. I think this is a great idea. So let's start with this. So I'll start with a little bit of history. So it all starts, the history about the satisfiability problem and resolution. And it all starts with the Davis-Putnam procedure, which goes back to the 1960s, which a few years later was reinterpreted by Robinson in a way as a proof system in the way we understand today resolution. So Robinson was thinking of propositional, first order logic, but the main engine behind the first order logic proof system was really a propositional proof system. And this is what we now call resolution. Now, several years later, when Cook proved that SAT is NP complete, we all know that his paper, he was interested in theorem proving procedures. That's the title of his paper. And one of the questions he was asking there is whether the Davis-Putnam procedure, this method that they had invented for solving satisfiability, whether it has hard instances, and that would be a consequence of P different from NP. So he was asking about explicit examples where this algorithm would have to run in exponential time. And this question, it took a long time to be solved until Haken in the 1980s, he finally showed that the pigeonhole principle, which is in a way can be encoded as a propositional formula, turns out to be hard for resolution, exponentially hard. And therefore, because resolution is seen as an abstraction of the Davis-Putnam procedure, it also showed that it's hard for the Davis-Putnam procedure. So this was the very first exponential lower bound for resolution. And after that, many things happened. So let's fast forward to the 21st century. And in 2001, something quite strange happened. On the one hand, people in systems were trying to implement actual, what they called SAT solvers, who were actually solving satisfiability problem for real benchmarks and real problems that happen to be interesting for industry and for software verification, hardware verification, and other applications. And the chaff implementation was the first evidence that in some sense, the satisfiability problem was easier than we thought. And even the proof search problem was easier than we thought, because these algorithms, when the formula happened to be unsatisfiable, were producing resolution proofs. And it's quite impressive that it can solve very big instances and find pretty big proofs. And this happened in 2001, and there was a lot of progress since then. But also in 2001, there was the first theoretical evidence that the proof search problem for resolution would have to be hard in the complexity theoretic sense. So this result of Aleknovich and Razborov gave the first conditional hardness result for the proof search problem. But of course, the progress in this SAT solving didn't stop. And one example I want to show is this, want to talk about is this 2016 amazing result where they, through a SAT solver, they managed to, and a lot of optimizations, they managed to prove a theorem in mathematics. In fact, a Ramsey theoretic statement called the Boolean Pythagorean triple problem. And this was an open problem in Ramsey theory, and they managed to actually prove it by a SAT solver, and the proof that it produced was an absolutely huge proof, like 200 terabytes. And this proof is in fact a resolution proof in disguise. And so in some sense, what happened here is that an absolutely huge proof for a problem that has many, many variables was found by an algorithm that supposedly is supposed to do exhaustive search. So what is happening here? How come we can find such big proofs for such a hard problem? So I want to try to shed some light onto this. So let's start by defining resolution. So of course, resolution works with clauses, and clauses, so this is just some notation. We have variables x1 to xn. These are Boolean variables. We have the negations, and this n is always going to be the number of variables. Clauses we make with these literals. These are disjunctions, and CNF formulas are conjunctions of clauses. Now, the resolution rule is a way to infer new clauses from old ones. So suppose you know that C or X is true, and you also know that D or not X is true, then you can infer that C or D must be true because X cannot be true and false at the same time. So this is a very simple rule for deriving new clauses from old ones. And in fact, this is a completely general statement that any clause that can be derived from your clauses can be derived by such a rule, such a simple rule. Now, this way we produce resolution proofs or resolution refutations. So we have a formula F, which we want to refute. We want to show that it's unsatisfiable. And the way we show that is by producing clauses one by one. Each clause is either a clause from the original formula or follows from previous clauses in the sequence by the resolution rule. And what you want in the end is to produce the empty clause, which would show that the formula is then unsatisfiable because it doesn't have any satisfying assignments. Now, the complexity measure that we are going to be interested here is on the length of the proof, which in this case is just the number of clauses that we see, in this case S. And now the resolution complexity of the CNF formula is going to be the smallest length among all resolution refutations. Now, one simple observation is that the resolution complexity of a formula is never more than exponential on the number of variables, unless it's actually infinite because it doesn't have any refutation at all, which happens precisely when F is a satisfiable formula. So we know that the resolution complexity cannot be more than exponential unless it's infinite, all right? So this is the measure of complexity. And now this is the proof search problem, naively formulated. It's the following. You're given an unsatisfiable CNF formula. You're promised that the formula is unsatisfiable, and your task is to find a resolution refutation of the formula. Now, an obvious observation is that, well, because the smallest resolution refutation could be, in principle, exponential, that's what Haken's theorem says. Now, this problem cannot be solved better than exponential in the number of variables, but that's not a very interesting observation because the reason for this is that there is no better output. So another question you can ask, which is a bit more meaningful in terms of the proof search problem, is whether whenever short proofs exist, suppose you're promised for some reason that short proofs exist, can you find them? Can you find them efficiently? So this, for example, doesn't happen in the case of the pigeonhole principle. That's not an example where this algorithm would be interesting. So you want to find short proofs when they exist. And so another way to formulate this same question is whether you can solve the problem in some reasonable time as a function of not only the number of variables and the number of clauses, but also as a function of the smallest resolution refutation of the formula. So it's easy to see that these two questions are the same by a simple padding argument. And whenever you can do this efficiently, we are going to say that resolution is automatable. And this definition makes sense for polynomial time, for quasi-polynomial time, or anything non-trivial, and is due to Bonnet, Pitassi, and Raz when they defined this concept. And since then, it's been studied in proof complexity a lot. So to repeat, we was going to say that resolution is automatable in polynomial time if you can find the shortest proof, you can find a proof in time polynomial in the shortest proof, okay? So now we have the definition, and so here's the result that we're going to show. We're going to show that resolution is, the proof search problem is hard because resolution is not automatable in polynomial time unless P equals NP. So this shows that it's as hard as it can be. Notice that this assumption is optimal because if P happened to be equal to NP, then of course resolution would be automatable by simply producing the proof bit by bit, asking an NP oracle, which under the assumption that P is equal to NP would be polynomial time. So this is an optimal assumption. This is an if and only if statement. But what if you assume something a bit stronger, like the exponential time hypothesis, then we can even show that resolution is not automatable in sub-exponential time. So again, so this is as hard as the problem can be. Now, but in fact, the way we show this gives us more, because here's the structure of what the proof is going to be. So we're going to find a map that takes CNF formulas into CNF formulas. So from F, we produce a formula G in such a way that satisfiable and unsatisfiable cases get this difference behavior. So if F is satisfiable, then the resolution complexity of the output, G, is going to be almost linear, so pretty small. But if F is unsatisfiable, then the output is going to have resolution complexity that is almost exponential. So this is a huge gap. And what this, on the one hand, this already implies the non-automatability result, because, well, suppose you could find proofs in time polynomial in the shortest proof. Then what are you going to do to solve SAT? Well, what you do is you produce G, and then you run your automating algorithm for time polynomial on this quantity. And if by that time you have found a refutation, then you know that you're in this case. But if by that time you have not found a refutation, then you know you must be in the other case, right? Because this gap is more than polynomial. Because the gap is more than polynomial, you can conclude that you cannot solve it in polynomial time. All right, so one thing to notice is that the formula G in the first case is always going to be unsatisfiable. That's the only way to have a resolution refutation of it. But in the other case, it could be that this formula is satisfiable sometimes. And in that case, the resolution complexity is going to be infinite, which is consistent with the fact that it's big, right? It's pretty big, infinite. All right, so another thing that this thing says is that, well, if you want to approximate the resolution complexity of a formula, then you cannot do it very well in polynomial time, because what this is showing is that the minimum resolution proof length cannot be approximated in sub-exponential error in polynomial time unless p equals np, because otherwise you would be able to distinguish the SAT case from the unsat case. Okay, so this is a corollary of the construction, and the automatability result was our original, the non-automatability result was the original motivation, but this is a byproduct that we get from the construction. So before I tell you how the construction is done, I want to tell you a bit what people tried before. And the thing is that this problem had some partial positive and some partial negative results. And that's what made the problem particularly challenging, because there were binding difficulties. So let's start with first the definition of what other proof systems, because the stronger results are going to talk about, these partial results are going to talk about other proof systems. So remember, the resolution rule is basically the one you see here. From C or A and D or not A, you can conclude C or D. And in resolution, we had that this A was a literal, X and not X. But in general, you can think of this as being an arbitrary formula. It doesn't have to be a literal. This is what's known in logic as the cut rule. And when you allow arbitrary formulas in your proof system, then you get a stronger proof system. And this is called the Frege proof system. And of course, when you allow more formulas than just clauses, then you need, besides the cut rule, you need some other rules to manipulate these formulas. But this rule is the really important one. And once you have this rule and you allow more general formulas, you get stronger proof systems and weaker as well. So resolution would be the case where you have the cut rule restricted to clauses. And we've already seen that. And now we have a hierarchy of increasingly powerful proof systems where instead of clauses, for example, we could allow KDNFs. KDNFs is a generalization of clauses, of course. One DNFs would just be clauses. And this would give the proof system that's sometimes called RES-K or KDNF Frege. And another thing you could do is you could allow your formulas in the cut rule to be formulas of some bounded depth. And in that case, you would be talking about AC0 Frege by analogy with the complexity class of AC0 circuits. You could allow your formulas to be threshold formulas because there's no reason why you have to restrict yourself to Boolean and or, but you can also have other connectives like thresholds. And in this case, that would be TC0 Frege. If you allow general formulas, you would get what's known as Frege. And you could even allow general circuits, that would be extended Frege. And this is a very powerful proof system where lots of things can be done. Now, what can be weaker than, so these are stronger proof systems, what can be weaker than resolution? Well, you cannot talk about formulas that are weaker than clauses. I mean, that would be quite silly. But one thing you can do is you can restrict the proof graph. So remember, the proof graph of a resolution refutation is the structure you have when you look at which clauses are used to derive which others, right? This is called the proof graph of the proof. And now when you restrict, for example, your proof graph to be a tree, you get what's known as tree-like resolution. And you could also restrict that to be not a tree, but for example, some kind of read once branching program or some restricted form of directed acyclic graph. And in that case, we would call it regular resolution. So these are weaker proof systems that people have been looking at. And the first positive result that was known on automatability was precisely about tree-like resolution. So in Beam and Pitasi proved in '98 that tree-like resolution is in fact automatable in non-trivial time. And this non-trivial time is some quasi-polynomial function of the size of the formula or the number of variables. And the log in the exponent, the log of the optimal proof. So this is a pretty strong result. It's saying that you can find short proofs in tree-like resolution in non-trivial time. And intuitively, the reason this works is because tree-like proofs have pretty good interpretation, and they can be interpreted as decision trees. And once you have trees, then you can apply methods of divide and conquer and things like you could do also in other contexts, like in learning. Decision trees are well understood, and similar techniques can be done here to get these positive results. For us, this is important because the upper bound shows that there is a short resolution refutation, but what we know from this is that we cannot expect this refutation to be, in addition, not only short, but also tree-like, because then we would be violating the exponential time hypothesis. So this is important information for us, that it puts a limit on what we can prove. So this was great. And now the question is, well, can you go beyond? Can you do something for resolution? And in fact, there is something you can do by the same techniques, but Bensesson and Victorson had a slightly different formulation of it. And so in general, for resolution, without any restriction, you can show that it is automatable in some non-trivial time. So let's see what this function is. You have number of variables raised to the square root of the number of variables times log of the optimal proof. And this k is just the width of the clauses. So in case of 3 CNFs, this would be just 3. Now this is a non-trivial upper bound because, for example, in the case of polynomial size proofs, which remember is one of the cases we're interested. So can we find short proofs when they exist? So what happens if you have polynomial size proofs? Well, you plug here polynomial and you get something like exponential in the root of n. And this is non-trivial exponential running time for a problem with n Boolean variables. So this is a non-trivial thing, and it's something that also puts some limits on what we can show, and therefore it's important for us. So, and the question was, well, can you improve on this? And is this optimal? What can we say about it?
Excuse me.
So this was about the positive results. Now about negative results. So the negative results are
Albert,
of the type.
just a second. I think someone has a question.
Okay. Yeah, just the previous slide. Does that imply that your reduction is actually optimal up to some log factors in the exponential?
Yes. So yeah. So this algorithm. Let's see if I understood the question. So this algorithm is, this analysis comes from the size width trade-off. So meaning that if you have a proof of size S, then you have also a proof of this width, the thing in the exponent. And once you have width, meaning the width of the clauses, how wide the clauses are. And this is known to be tight. So it means that this square root n log S cannot be improved by the same method from which this theorem has been proved. Okay. So I hope this answers the question. And
looks like yes.
Okay, so let me continue. All right, so this was about positive results, so some algorithms for automating resolution. So what about non-automatability? What can we say? And so the first result along these lines was this result of Krajenček and Pudlak, also in '98, where they proved that the strongest possible proof system that we considered, this was reasoning with circuits, extended Frege, is not automatable in polynomial time unless RSA is broken by polynomial size circuits. So RSA is the cryptographic system. And so this is putting already some limitation into the proof search problem for a strong proof system. But one thing to notice is that this assumption is crypto, is not a worst case assumption. Well, it is a worst case, but it's crypto in the sense that it's something that is not known to be NP hard or any harder than that. And it's far from optimal in the sense that if you assume that RSA is broken, then it doesn't say anything about the automatability of extended Frege. So this is something that we find important. Another thing is that this thing has been improved for other proof systems like for Frege or TC0 Frege or even AC0 Frege. But the assumptions are still crypto, and in fact, they are stronger and stronger assumptions that you need for this to be true. And in any case, this AC0 Frege, while it's getting closer to resolution, which would be depth 1, it's still far. So the hardness you get here is for pretty big depth under a very strong assumption in crypto. So this was this was done also around the same time at the end of the 90s. On the other hand, there is some negative results for resolution itself. We already mentioned this Aleknovich-Razvorov non-automatability result for resolution. They prove that it's not automatable in polynomial time unless WP is tractable. WP is a class that appears in parameterized complexity. And so one thing to notice is that this result says nothing about non-automatability in quasi-polynomial time, for example. So we cannot replace this by something and get quasi-polynomial time by the same technique. In fact, this was tried just very recently. And the best they could get by using the same methods from this theorem is that if you assume the exponential time hypothesis, then all you can rule out is algorithms that run in time this much quasi-polynomial. So n to the log n. And so this is what you get from these methods. But in addition, one thing is that this theorem, and this is already in the Aleknovich-Razvorov paper, applies even to tree-like resolution. So in fact, resolution is not automatable. Tree-like resolution is not automatable in polynomial time under the same assumption. And recall that tree-like resolution is automatable in quasi-polynomial time. So there's a good reason why these methods cannot give better than these lower bounds, because in fact, there is an upper bound of n to the log s. So this means that if we want to show something like cannot be automated in sub-exponential time, then we need to use completely different methods. And this is in fact what we do. So the rest of the talk, I'm going to now focus on our own construction. So remember, this is what we want to do. We want to start with an arbitrary CNF. We want to produce another CNF G with this behavior. So the resolution complexity in one case is small, in the other case is big. And recall, this is almost linear and this is almost exponential. All right, so how do we do this? In fact, it can be very easily described. So this is a first take because this is the first thing we tried and it didn't exactly work, but the intuitive idea is this. So you take your formula G to be a formula that says that there is a refutation of the formula f of polynomial length and this fixed explicit polynomial n cube. So notice this is an existential statement. So it's something you can formulate as a satisfiability question. And therefore you can talk about the resolution complexity of such a formula. And now what we want to answer is these two question marks. So, well, first of all, why do we take this formula? And why should this be an important formula? But the other thing is, would it give this behavior that we want? So let's think about it for a second intuitively, what this is happening, what this is saying. So when f is satisfiable, then it is impossible that there's going to be a refutation of f, right? If f is satisfiable, there is no refutation. So this means that in the F satisfiable case, the formula G is unsatisfiable. So that's a first necessary condition in order to have a small complexity. But in fact, from the fact that F is satisfiable, it has a satisfying assignment. From this satisfying assignment, you should be able to witness the unsatisfiability of G, right? Because if someone gives you a candidate refutation, then you say, okay, I have a satisfying assignment, so I just go clause by clause and until I find a mistake in your proof, right? So this is the intuition why this should work, because if F is satisfiable, the satisfying assignment should give you a handle on what is the small refutation of G. So once we notice that this is what we want, then and we said, okay, can we prove this? And then we would be done, because the other part, well, no, the other part is also requiring proof, but the intuition is so strong that it looks like this should work. So let's start with the first part. Can we actually prove this intuition? And in fact, we can do this. We can do this, and since a long time, we have been able to do this, in fact. And this goes back to this concept of metamathematics known as the reflection principle for a proof system. So the reflection principle of a proof system is nothing else but its soundness. So look at this formula here. So this formula, this is a CNF formula. It has variables for encoding a CNF formula X. And then it has variables that encode a truth assignment for X. And then these clauses will say that Y satisfy X. And the clauses here, ref for refutation, state that Z encodes a resolution refutation of X. Now, of course, these two things cannot be true at the same time. You cannot have Y satisfying X and Z refuting X. So this is a CNF that is unsatisfiable, and the unsatisfiability is in fact expressing the soundness of the proof system. Now, for resolution in concrete, this has a very explicit form, and we will use that. And in fact, Steve Cook already in his 70s, in his papers of the 70s, was using such explicit encodings for, instead of for resolution, he was doing it for extended resolution. But for us, we want to do it for resolution. So, and we need an explicit encoding because we need to prove explicit upper bounds and explicit lower bounds. So let's go a little bit through the encoding, even though it looks a bit tedious. I think it is useful to do because to tell you the intuition of the proofs. So recall, refutations are described, I mean, they are just sequences of clauses. So this Z is going to describe such a sequence. This X is going to describe the original formula F. And this Y is going to be just the truth assignment. So the first thing, we have a variable, for example, that says that for describing the formula F, we say that, well, the ith clause in the formula contains the variable Q with sign B, which could be positive or negative, 0 and 1. Now, this is the way to describe this CNF. For describing the truth assignment, you just say that the variable evaluates to 1, and that's a new variable for every Q. And now let's describe this refutation. So for example, I will describe this variable here. So this variable says that the ith clause is inferred from the clauses J and K by resolving on variable XQ. So this would be describing one of the steps of the refutation. So this, when this is true, then this is indicating that these arrows are present. Another kind of clause variable you can have is that you describe which are the literals of every clause. And finally, you also need to say, for example, when a clause is one of the original clauses of F, you need to say which one it is. So for example, Zij will say that the ith clause in the refutation is the jth clause of the formula F. And now the clauses of ref are just going to axiomatize these meanings for these variables. And this is completely straightforward. You can do it the way you prove, for example, that SAT is NP complete is by describing computations of a Turing machine. Here you do exactly the same. You just describe such structures by clauses. Okay, so we have this is called the reflection principle for resolution. And as I was saying, we knew that in fact this thing is relatively easy because since 2002, we know that this unsatisfiable formula has polynomial size refutations. not in resolution itself, but in slightly above proof system. And it's proof system that works with 2 DNFs. Remember, if we work with 1 DNFs, then we're working with clauses, that's resolution. So this is not easy for resolution, but it's easy for 2 DNF Frege. And this is essential for our proof. So let me give you a sketch of how this works. So here's the proof idea of how to refute the reflection principle in 2 DNF Frege. So you start with the clauses of SAT and the clauses of ref. And now recall that Z is describing such a thing, a sequence of clauses. So now we are going to derive 2 DNFs. These are 2 DNFs. And the ith DNF is going to say that the ith clause in your refutation is made true by the assignment Y. Okay, so how is this done? For example, let's look at the first one. The first one says that there exists a variable Q from 1 to n that is evaluated to true by the truth assignment and that appears in the first clause with sign 1. So if this happens, if it appears positively and it is evaluated to true, then the clause, of course, is made true. So this is one way to make it true. Another way to make it true is by saying that there is a variable that is evaluated to false by the truth assignment and it appears negatively in the clause. And this is in fact the only 2 ways to satisfy a clause. And this way you are saying that the first clause in the refutation is evaluated to true by Y. And this is not at all difficult to derive from these assumptions. And in fact, this is just some bookkeeping. You need to manipulate clauses until you get such a thing. So once you have, for the first clause, you can derive it for the next one. And for that, you use the soundness of the resolution rule. And it's also, again, a matter of manipulating symbols. Now, what happens when you reach the end? So the end is going to be the last clause. So this is with S. So we're talking about the first clause here and the last clause there. And this is saying that the last clause is satisfied. But what does the ref formula say about the last clause? So the ref formula, it says that what we have here is a refutation. So in particular, it says that the last clause is empty. How do you say that something is empty? Well, by saying that these things are false. So all these things are false. And these are things that appear already in the ref formula. So we have derived this thing that expresses that the last clause is made true, but at the same time, we know that this thing is empty. So we have produced a refutation. So basically, this is the idea of how you prove the soundness of resolution in 2 DNF Frege. Notice that these are 2 DNFs. All right, so this is important for us because what does it say? Well, it says that we already have 1/2. We have 1/2 of what we want. So remember, when F is satisfiable, we want our G formula to have resolution complexity small. Our G formula is the statement of that F has a resolution refutation, which is an impossible fact because F is satisfiable. So how is this small refutation happening? Well, here it is. So suppose Y satisfies F. And now you take the reflection principle and you instantiate X by F, the Y you instantiated by the satisfying assignment, and the Z you leave free. And now this is our G formula, which notice that this is made true. So essentially this is equivalent. This is just true and something. So you're left with something. And now this has a small refutation because the whole conjunction has a small refutation, and in particular the restriction also. And now we look at all the clauses that, or all the 2 DNFs that were in that appeared in the proof. And we notice that now they are no longer 2 DNFs, they are clauses. Because what made them 2 DNFs was a conjunction of one variable and another variable, but now this is not a variable anymore. It's a concrete truth assignment. So these 2 DNF became a clause. And therefore the 2 DNF Frege proof was in fact a resolution proof. So this is how we get that the refutation statement G has a small resolution refutation when F is satisfiable. So this is formalizing the intuition that we had in the beginning. So this is great. So we have 1/2 and we have the half that we think is the correct one. This is saying that the satisfiability gives you the witness to this existence of Short's proof. So can we show the other part? And this other part, this Z is a polynomial length. So can we prove this? And so this took us a while, and in the beginning we didn't know how to do at all. So here is the intuition why we thought it could work. We could do it at least. So we want to show that this is hard to refute. Now F is unsatisfiable, okay? So we want to show that this is hard to refute. So one way to show that it's hard to refute is, for example, if it's satisfiable, then it's impossible to refute. And we know that this will be satisfiable if instead of n cubed, we allow 2 to the n size of a proof. And that's because every formula has a refutation. Every unsatisfiable formula has a refutation of length 2 to the n. So we have a formula that we want to show hard, and we know that if we make this thing larger, then it's impossible. So now what it's left with is whether we can show that these two things are not distinguishable by small proofs. And basically, this is what we tried for a long time. And so we failed, but we failed for this formula, and we had to modify it a little. So before I tell you how to modify it, let me tell you something we succeeded to do. So what we managed to show is a width lower bound. So we managed to show that these formulas are going to be hard for width. So they require large width refutations. So what do I mean by width? And how do we prove width lower bounds? So this is a generic refutation. So from C2 and C3, you can derive a D1 and so on until you get the empty clause. Now, you can think of refutations as solving what's known as the falsified clause problem for your CNF by turning the proof upside down, and you think of it as a query algorithm. So this is what I call the query algorithm, where you query a variable X, and then according to whether it's true or false, you go left or right, and you keep querying variables and you keep going to the part that is falsified. And there is always one that is falsified until you reach a clause that is made false by the answers that were given during the algorithm. So it turns out that a small width refutation, which would be a refutation where every clause here has small width, corresponds to small space query algorithm for the falsified clause problem. Now it's not a generic query algorithm, it's just some people call subcubical query algorithm. It's a special type of query algorithm, but still a query algorithm. So what we want to do then is if we want to show that such a thing doesn't exist, we need to prove a lower bound for such an algorithm. And so in other words, if we want to prove a width lower bound, what you need to find is an adversary strategy that is going to answer the queries and survive without falsifying any clause under the assumption that the clauses in the middle have small width. So we want to find this adversary strategy to get a width lower bound. And so how do we do that? So here is one picture to show how we can give an adversary strategy in the case of the ref formulas. So remember, we want to show that this doesn't have a small width refutation. And so we're going to play this game where someone, so the prover is asking queries about the variables of this formula. And we as adversary have to give answers to these queries. So for example, these are the variables that the prover can ask, and we think of it as representing a refutation. It's a refutation of F, right? This is what the variables are representing. So whenever we're queried about what is this clause or what is the literal in this clause, we need to answer and say, well, this literal is XQ, for example, or whatever. The way we answer it is by moving to the exponentially big refutation for F that we know exists. We move there, we see what this canonical refutation says, and that's what we reply to, or as an adversary, that's what we reply to the query. Now, of course, why can we do that? Well, we can do that because we know that the prover is using small width. So it's using windows that are very small. They are only n, and we're taking our refutation to be of length n cubed. So by placing it in a proper way, and what you end up showing is that this set of variables can be pretended to be, in fact, you can pretend that it is set, it corresponds to this huge exponentially big truth assignment. So basically what we're showing is that the formula that we want to show is hard. We show that it's indistinguishable from a formula that we know is impossible to refute. And we do that because they are indistinguishable by width and local views. This is, if you understand what I mean by local views is that we only query few variables each time. We only remember few variables each time. All right, so we have a width lower bound. And so width lower bound, is it going to give us what we want? Well, it gives something. It doesn't give exactly what we want yet. So if f is unsatisfiable, what we want is that the resolution complexity is exponential, but what we can get is that at least that the width is linear in n. Now, the width being linear doesn't imply immediately that the size is exponential. There are some theorems that connect width and size, but this width lower bound is not strong enough, because in fact, this formula has to be polynomial, and so the number of variables is going to be at least cubic, and the width lower bound is not more than linear, so this gap is too big, and therefore we don't get the exponential size lower bound from the width lower bound. So this is in some sense a failure. We haven't got where I wanted. So what we're going to do then is, instead of looking at this very clear statement, this is the G that I've been talking about, we're going to look at something a bit stronger. So this is a method that sometimes it's been called a lifting in proof complexity, but it actually goes back to Krajicek in proof complexity. It's called the method of relativization. So we're going to make the formula slightly harder. And here is what this formula is saying. It has a very clear meaning. So besides the variables that describe the refutation, we're going to have new variables that are going to say that the clauses in the refutation, some of them are active and some are not active. And you should think of these variables as if they were set at random. So you say, out of all these S clauses, some of them are going to be relevant and some others are going to be completely irrelevant. And the way you say that they are irrelevant is by saying that the meanings of these variables only make sense. So they only have a meaning if the clause is active. So if I is an active clause, then it is inferred from the J and dk and the rest of things. So this way we have some relativization of the refutation to a subset of the clauses. Okay, so why does this help? And well, first of all, how do you formulate these as clauses? Well, you need to say that something is active, otherwise everything trivializes. So you say that the last clause is active. You also need to say that activity propagates, because if something is active and something is derived from something else, then the thing you derived from must be also active. So this is some closure property that you impose. But then you also require only proof shape on active clauses. So if I is active, and I is derived from J and K, then J has, this says that it's derived from some resolution, some literal or whatever. All right, so this is the meaning of this formula. So why does this help? Well, it helps a lot in the refutation in the lower bound, because we can now apply a random restriction that is going to convert this relativized formula into our original ref formula. So it was not a waste of time to discuss this formula in detail, because so what is the random restriction? Well, the random restriction is going to set the formulas, the literals, into active or inactive with probability 1/2. So for example, first of all, you need to say that the last clause is active. That's required, but all the others, you're going to set them active or active or inactive with probability 1/2. And now for the things that happen to be not active, then the corresponding variable is irrelevant. So you can set it completely at random as well. And this is crucial, because then this will simplify a lot our refutation. And what happens with the things that happen to be active, like if Zi is active, then you need to make sure that it satisfies the closure property. So for example, if if I is active, but J and K are not both active, then you should make sure that this is not set to true. So you have the closure property. So this is a random restriction that is the meaningful one, and it's going to have this property. So if you start with a short refutation, so small now means short in terms of length, not width, but length. And you apply this random restriction, then with very high probability, this is exponentially small, and this is the number of clauses. So with very high probability, what is left is going to have very small index width. So what is the index width? We were talking about width, but in fact, the width lower bound that we proved was not only on the number of literals, but even on the number of indices, and indices are these i's. So the lower bound we proved shows that you must have at least n indices in any refutation of this. All right, so with very high probability, we have something that is impossible if S is small. So we get our size and lower bound. So how small should S be to get a contradiction? Well, it should be smaller than the inverse of this exponential. So, all right, so this gives you the lower bound and should be wrapping up soon. So one thing we shouldn't forget is that, okay, we changed the formula. So what happens to the upper bound? Do we still have the upper bound? And that's essential, right? We still have to have the upper bound. And indeed we do, because now let's look at the reflection principle again, but now we're talking about not proper refutations, but about relativized refutations. So refutations on a subset of active clauses. And you want to still refute this, and that's perfectly possible by the same proof, because the only thing you say is that, okay, so remember this was saying that the first clause is satisfied by Y. So now you say that this is the case if the first clause is active. So if the first clause is active, then it is satisfied. And you do that for all the others. If the ith clause is active, then it is satisfied, and so on and so forth. And you notice that this is still 2DNF formulas. So we still have the kind of argument that we had. And that when you plug here a formula F and its satisfying assignment, this thing reduces into a resolution refutation. So if we put everything together, we get what we wanted. So now our G is no longer the standard ref, but it's the relativized ref. On the one hand, if it's satisfiable, then it has small resolution complexity by the argument of the previous slide. And if it is unsatisfiable, then by the random restriction argument, it's going to be exponentially hard, or even infinite in case it happens to be satisfiable. So we have exactly what we wanted, and this finishes the proof. So let me conclude now. So let's go back then to the beginning. We had this history. So we had this tension between implementations of SAT solvers that were finding short proofs. Well, they were finding proofs pretty efficiently. But on the other hand, we had evidence that this has to be hard. And then the progress said that you can even find pretty big proofs. But one thing I want to say is that this formula, in fact, is the formula. If you want to brute force on this, then it's not on the proof is the brute force proof is not going to be 200 terabytes. It's going to be absolutely huge. It doesn't fit in the universe because the number of variables of this formula is something like 7,800 or something like that. So this means that the brute force proof is going to be 2 to the 7,800, which is absolutely ridiculously bigger than this. So this means that these SAT solvers are actually finding clever proofs of this statement. And this is quite amazing. And while on the other hand, what we proved here is that the proof search problem is as hard as it can be. So the tension that we had in 2001, it's now more evident than ever. And this is something we should clarify. So there's a lot of room here to understand how these SAT solvers are working and why they are so powerful. But this is something that we should discuss in another talk. So I'll finish here. Thank you very much.
Okay, everyone, thanks to Albert. And I guess we'll take questions if there are any. So if you have a question, maybe raise your hand or write it in the chat. Okay, I'm not seeing anything from anyone. Okay, so I had a question. I guess it's pretty open-ended, but what are the open directions in terms of like the unsettled questions in terms of hardness of finding proofs? I mean, is there concrete progress to be made?
Yes. So now one thing is that the fact that resolution is not automatable doesn't say anything about stronger proof systems. Because intuitively it should be harder, but the theorem itself doesn't say that. So the question whether, for example, a stronger proof system like polynomial calculus or sum of squares proof system is automatable is not answered by this work. On the other hand, polynomial calculus seems to have been solved already. So some group has shown that it's not published yet, but I've heard that some people have shown that polynomial calculus would not be automatable under the assumption P different from NP by the same kind of proof modified for polynomial calculus. On the other hand, for sum of squares, this is open as far as I know.
I see.
So this is one thing.
So the fact that these proof systems capture resolution isn't enough to mean that the theorem that you proved applies to those?
No, because
you may have shorter proofs.
So the positive case, it happens, right? So if F is satisfiable, then you have a short sum of squares proof or refutation of this. But in the unsatisfiable case, this lower bound is only for resolution. So what we would have to do is prove a lower bound for sum of squares refutations of this statement.
I see.
And this is conceivable. We don't know that it's easy. It's probably not easy, but we don't know how to show that it's hard.
Okay. Okay, makes sense. I see on the chat there are a couple of other people who asked questions, so I'll unmute them one at a time. I'll start with Gopal. Okay.
Yeah. So is there a particular reason that you picked that the length of the refutation must be n cubed? So why didn't you pick something else? What motivated you the selection of n cubed?
Yeah, a good question. So this n cube is for the sake of the talk. In fact, the optimal bound that we can get here is 12n squared. So it's quadratic, is the best we can get. And the reason, so by the way, this n cube comes here, you see this is n square width and n height. So that gives you the n cube. This is supposed to represent n square closest. And the reason we need this n square, or in the optimal case, it would be something like 12n, is because we need to have enough room to simulate these huge layers. So this is a narrow layer, this is 12n, and this is an exponentially big layer. So, and in fact, so in the beginning, we cannot do this because it's a narrow thing. So here the answers of the adversary strategy are just going to be the identity. But after log n steps, this is going to be large enough. And then if we leave enough room, so remember this width is n, and this is 12n. So here we have room for 11n closes, and this room is what allows you to simulate these huge layers into small layers.
Okay.
That's the
Thank you.
Okay, now we had a question from Clement as well. So,
hi. So sorry if I missed that, but in the reduction you seem to give even more refined correspondence between the exponent in the ETH and how automated resolution would be based. Is that right? For example, like if ETH holds with like that particular exponent, that means that it is that hard with like a corresponding exponent to do automated resolution.
Yes. So let's see. So this is the best gap that we can get. So if you assume ETH, okay. So here you have to, in order to know how hard is it going to be to automate resolution, then you need to know how big this polynomial, I mean, there's a blow up here from F to G, there is a blow up. So if this blow up, we know what it is. It's something like cubic or quadratic or something like that. And therefore that puts a limit on the ETH, on the automatability algorithm. saying that if ETH is true, then you cannot automate better than exponential with an exponent that is something like 1/6, I think. Okay, so you cannot automate in time 1/6 in the size of f. Yeah, so that's the the hardness you get. If you improve on this polynomial time, if you, instead of cubic or quadratic like you have it linear, then you also improve on the hardness.
Okay, any other questions in the chat? Okay, if not, thanks again so much, Albert, for the lovely talk, and see you guys in 2 weeks for Henry Yuan's talk.
Thank you.
Okay, bye.